Last time.
Photosynthesis.
Hi there. I'm a Pang. Today, we're going to be talking about vacuums. What is a vacuum? Well, to put an image in your tiny little head there, a vacuum is a pocket of space with absolutely nothing in there. Let me explain. I will explain vacuums with this. This is a capsule. Inside of this capsule is a bunch of marbles. Now let's imagine these marbles as subatomic particles in the air, or molecules, if you will. If we close this up, the space inside the capsule would be like our atmosphere. It has a lot of stuff in here, so this is not a vacuum. However, if we open it up and empty it out so all the particles are gone, close it back, the area inside of this would have nothing in it. No particles, nothing. It would be a vacuum. Now, what do we think when we think of a vacuum? Maybe this. But did you know that things such as this, and even the scientific things like this and this, all employ the idea of a vacuum? And who can we forget? Even this. Let's begin with something simple. Let's talk about how a vacuum works in a context that you guys might understand. An actual vacuum cleaner. It's a little bit complex. I mean, come on, look at this. What sorcery is this? But you'll get it soon. Explain how vacuum works with an actual household vacuum for you guys. First of all, you need electricity to work a household vacuum. This electricity is connected to the outlet and the vacuum cleaner, which starts a fan. Now, this fan is slightly angled. They're in there, and it will spin. As it spins, something called the Bernoulli's principle happens. Bernoulli's principle is essentially a divide of higher pressure and lower pressure. Now, this principle states that higher pressure will want to rush into a lower pressure to even it out. Now, if we take this, the vacuum would have a lower pressure in here because of the fan. Because of lower pressure, the lower pressure also means that there's less stuff in there. Remember when we said about vacuums, they have nothing in there. So if there's less stuff, there's a partial vacuum in the vacuum cleaner itself. Now, applying Bernoulli's principle and partial vacuum, the air we want to try to get in to even itself out, because the outside is ambient, which is normal pressure. Now, all this normal pressure, we want to fill that out because it's slightly smaller, about 20% less than outside. So all the air we want to rush in everywhere and try to fill up that place. So that's how vacuum cleaners suck through here, because all the air rushes through the opening and in to the lower pressure chamber. This similar concept can be applied when drinking from a straw. Atmospheric pressure pushes down on a liquid. When you begin sucking, you create a partial vacuum in your mouth, which has a smaller pressure than the outside. This creates a pressure gradient, which makes a force. This force can be represented with the equation that difference of the pressure times the area. And we can't neglect that the liquid has a weight of its own, which creates another force downwards. This can be represented with the equation the volume times the density. times the force of gravity. If we set these two equations equal to each other, and then rearrange it, we are able to find the height that the liquid can travel up the straw. Did you know? Let's jump to the lab for a bit. What I have here is a mercury barometer. A person named Evangelista Torricelli, an Italian physicist and mathematician, invented this in 1644 when Galileo Galilei advised him to use mercury in his vacuum experiments. Torricelli filled a 4-foot-long glass tube and inverted it on a dish. He filled it up with mercury, and he observed that there was mercury still in the tube and not all of it had escaped. And he also saw that there was a vacuum at the end of it. This became the first barometer, otherwise known as Torricelli's tube. Now, this height of the mercury is 760 millimeters. This is the standard atmospheric pressure that we experience on our everyday lives. However, this height would fluctuate from time to time depending on where on Earth you are, or even what time of day, and because the air changes around us. Another fact! The theoretical maximum of water traveling up a tube is 10.3 meters. Don't believe me? Let's plug in all the numbers we have with the formula that we learned before. Atmospheric pressure, perfect vacuum, density of water, and gravity. When we punch in all the numbers right and calculate it, we get 10.3. The theoretical maximum of water traveling up a tube in a perfect vacuum. Speaking of which, a perfect vacuum is a place where there's absolutely nothing in there. But we can come very close to it with the help of these things. This is a vacuum chamber. Specifically, this is an ultra-high vacuum. Ultra-high vacuums have the capability of sucking up a lot more particles than a normal vacuum would. By comparison, atmospheric pressure outside this vacuum chamber would be more than 1 billion times that of the inside. Now, let's show you what some things could happen in a vacuum chamber.
Hi, I'm Joanna.
And I'm Steve.
They're my minions, and they're going to show you one property of a vacuum chamber. Freezing nitrogen.
Once we begin to remove air from around the liquid nitrogen, it becomes easier for the fastest moving particles to escape. The fastest moving molecules are the ones with the most kinetic energy, so when they leave, the average kinetic energy of the remaining molecules drops. That means the temperature drops. Eventually, it gets cold enough that the nitrogen freezes. It just takes a minute. There's some, and there it goes. Come on. Oh.
That was close.
It was.
Oh, now it's working.
Now we've got it.
Wow, look at that.
It's like Jiffy Pop.
Uh-huh.
Perfect. Now I have some frozen nitrogen all to myself. Wait, no!
As soon as we let the warm air back into the vacuum chamber, the nitrogen melts away.
Sadly, Joanna and Steve will not be working with us any longer. Luckily, I have some other people to help us with an opposite kind of experiment. We're going to boil water in a vacuum chamber. As the assistant pours water in and locks it in the chamber, she lowers the pressure, and at a certain point, about 20 millibars, the water begins to boil at room temperature. Like there. Now you might wonder why this is so. Usually when we say boiling point, we only think of temperature. However, this is only half true. Boiling point of fluids is intrinsically linked to the pressure of its environment. Let's take a look at this graph. This clearly shows that water boils at a lower temperature at lower pressure and higher temperature at higher pressure. It's undoubtable that they're intrinsically linked. Now that we've learned some of the stuff that could happen in a vacuum, let's go to the closest thing we have to a perfect vacuum. Outer space. Now, I say closest thing to a perfect vacuum because outer space still has tiny little particles in it that we can't see. And it could never truly become a perfect vacuum, something that doesn't have anything in it, because it has these small particles in it. However, because it has no air pressure, it acts like a perfect vacuum. So I'm going to call in Michael from Vsauce to help me out with a segment I call Dangerous Science, as to what would happen to a human being if they were let out into space, naked, without protection. Take it away.
The air in my lungs and digestive tract would quickly rush out. Moist, soft tissues would rapidly lose water. My mouth and lips and eyes would dry out and swell. As water was pulled to the surface of these things, it would vaporize, and the decrease in its pressure would cool my mouth and eyes to near freezing.
Yikes. I certainly don't want to get caught up in that kind of situation. Luckily, I don't have the money to go up there. That aside, that's all the time we have for today. Back to work.